All right, so when I'm finding my common denominator, and by the way, this coefficient's just going to hang out here and not do a whole lot of anything. Please don't talk while I am. It makes me feel like I got to talk louder, and then we're in a competition, and I like to win. So my x to the 4th needs to be multiplied by this factor that was missing, 2x squared plus 1, and that's going to be minus. And my x cubed minus x squared has to be multiplied by the factor he was missing, which is 2x cubed minus 1. You okay there? So when I go to multiply and put all these together, I end up with, let's talk about my numerator first. I wind up with 2x, add my exponents to the 6th plus x to the 4th, and it's minus everything that's inside here. So that's going to give me 2x to the 6th. That's my first terms. My inner terms are negative 2x to the 5th. My outside terms minus x cubed, and my last terms plus x squared. And that's going to be all over, don't forget about your 1/2. And I have 4x to the 5th, right? 4x to the 5th plus 2x cubed minus 2x squared minus 1. How am I doing? All right, so now I'm going to combine like terms and see what I'm left with. Don't forget about your 1/2 times. Let's talk about my numerator. This negative is going to make him negative, him positive, and him negative, and remove these parentheses. Are we okay with that, fuzzy math? So that's going to give me 2x to the 6th plus x to the 4th minus 2x to the 6th. Oh, hello. Goodbye, leading coefficient. Plus 2x to the 5th plus x to the 3rd minus x squared. And that's going to be all over 4x to the 5th plus 2x to the 3rd minus 2x squared minus 1. Hey, here's a crazy thing that just happened. I thought this was an x to the 6th problem, but it's not. And then I'm like, oh, who's next biggest? Not you. You. Wait a minute. And you? They're the same. So now all I need to do is care about their coefficients. Because all this blah, 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 chicken feed. All I care about is the highest power. So now I've got basically 2x to the 5th over 4x to the 5th. Don't forget about who? So your limit as x approaches, are we going to infinity? How fun is that? Very cool, right? Okay. I feel bad for the A's because they didn't get theirs worked out. Hey, partners, work it out right now. So, she wants to talk about the slant asymptotes. And I'm with her on that because those are the hard ones for sure. So, when we have a slant asymptote, that graph that we had before, let me pull up that Desmos one, because that was a lovely sample. Can she find it? This one? Okay. And I want to go in here, and I want to make this much thicker so we can see it. Okay. It's like I wish everyone was listening. Like, what do you want for Christmas? I want my class to listen. So Adrian and I were like, okay, as x approaches infinity, where's my graph going? Stay with me here. All eyes on me. Spin around if you need to. There we go. As x approaches positive infinity, where's my output going? Say it out loud. Okay. As x approaches negative infinity, where's my graph going? Okay. So Adrian's like, I don't get it, because when we talked about this says, I don't get it. Because we just said and agreed on infinity and negative infinity, but this sheet says does not exist. I'm like, oh, that's funny. And then I thought about it, and I know why. It's right. And I know why. And we're going to go back to so if you're finding the limit and it's not about x approaching one or the other, if those limits don't match, doesn't that take us back to what we were talking about weeks ago, right? If those limits don't match, if those functions are not heading in the same direction. Now you're like, okay, wait a minute, what about the ones where limits are approaching the horizontal asymptotes, the values match? They're both 0, or they're both whatever that A over B value is. But if your limits are not approaching the same value, if you don't get the same, whether x is approaching positive or negative infinity, then you have to say that the limit of that value does not exist. Adrian, does that make sense? Yeah. Okay, hop back to your seats. Quick, like a little bunny rabbit. Let's go. Rule number 1 of finding limits is plug it in. Rule number 1 of finding limits is plug it in. A limit exists if the limit as x approaches from the negative direction and the limit as x approaches from the positive direction. If those two limits match, then I have a limit. So our piecewise functions mess things up, but basically our run-of-the-mill equations and polynomials, you can always have that limit exist coming from the other direction. Sometimes we end up with a crazy indeterminate form where I get 0 over 0, and now we're talking about these crazy indeterminate forms where I get infinity over infinity, and you're like, what the heck do I do with that? So it's your job to use algebra to start messing with it. So it's your job to mess with it. So we're going to call it manipulate it, because algebra lets us do things that's going to make it go crazy. What's my first choice when I'm looking at it? First thing I can do to an expression that's giving me an indeterminate form. What's the first thing I can do to it? I can factor it. Because what I'm hoping is if I factor it, then one of those x's, particularly the one that's in the denominator messing everything up, I'm hoping he goes away. I'm hoping I can cancel him out. See you later, Sally. Away he goes. What if I can't factor it? What is my next possible option? The conjugate is one. Good, Veronica. And the conjugate is the one that deals with my plus minus pattern. That's the one that makes that middle term cancel out. Hey, the conjugate is our best friend whenever we're talking about radicals and i's. We're not going to have a lot of i's in this. So we'll just go ahead and make sure you know that that's going to help me eliminate my radicals. And what did we just do for this last one? What did we just do? Common denominator. Veronica's got her game on today. So when I find a common denominator, what I'm looking for is one of those x's to simplify. I'm looking for one of those x's. Whichever one is messing me up, I'm hoping he's going to go away. All right. So rule number one here, plug it in. If you put -3 in here, does it give you something that you need to mess with? And if it does, let me ask you something. What's your first thing that you're going to do? If you end up with 0 over 0, or you end up with infinity over infinity, go and see if you can mess with it. This becomes x plus 3 and x minus 5. This becomes x plus 3 and x minus 7. Once I get rid of those x plus 3's, then that thing that was making my denominator go wacky, get rid of it. Unplug it. Ah, see you later, Sally. So now when I put my -3 into that equation, oh, plus 7. Go put some more together. Now when I put my -3 into that equation, I get -8 over +4, and that's how I get a limit of -2. All right. Because I have a higher power in my numerator than my denominator, we're going to say that as x approaches -infinity, so does my function. 3 and 4. Now, one of two things are happening. You're checking the work that you did since last class, and you're verifying whether or not you understand, trying to find your mistake, ready to ask the question if you don't understand. That's the first thing. That's the ideal thing. That's what every teacher hopes for. Please let them do their independent practice outside of class, so they have some thought, some experience, to know what they do and do not understand, so that they come back to class ready to ask an intelligent question. That's a teacher's prayer, administrator. The second possibility is you're sitting there with a blank worksheet because you read new calculus. If that's true, you're at least writing down the answers and putting a box around them, because then when you go back to do the work, you're going to try to make sure you understand how that answer is possible. Hey, you got to do the work. If you do the work before you come into class, you have the opportunity to ask questions and we figure it out and talk together. And class is more exciting and interesting and engaging for everybody. That's how it works. An academic buzz of learners. If you didn't do the work and you're sitting there like a bump on a log, then you owe yourself some work. Who do you do homework for, me or you? Yeah, you do it for you. Don't do me any favors. You do homework for you. Either you want to understand it or you don't. Either you want to test to see whether you know it or not. And if you haven't done this homework yet, my God, at least copy down the right answers so that when you do it, you know whether you're doing it correctly or not. Sometime between now and your test, you got some calculus to work on. Those are the answers to 3 and 4. Here's the answers to 5 and 6. Here's the answers to 7 and 8. For the folks that did their homework, what questions do you have? Go.
for 4 and 6.
Alright, so for 4 and 6, are you ready for how easy 4 is? Or 3, you understand? 4 and 6. Okay, when we talk about the cosines as x approaches pi over 6. So the oops, let me get my pen. Okay, so the cosine of pi over 6 over 4. There's no variables in the denominator, no problems with the denominator. I don't have to worry about the trig rules because this is a fine polynomial that doesn't affect anything. So I go to the cosine of pi over 6. I'm going to look at my pi over 6 family, and my cosine is root 3 over 2. So, root 3 over 2 divided by 4.
That's why I got
Yeah.
over 8.
Yeah. I agree with you. We'll check that because I like root 3 over 8. We're going to star that because I question that key. I like your answer better. All right, and then 6. Okay. Are you ready for this one?
No.
Just look at, why does it do that? Just look at the first term. The square root of 9x to the 6th is 3x cubed over x cubed. So we're going to pay attention to where that horizontal asymptote is. And as x approaches infinity, my graph is going to approach the line y is equal to 3. Does that make sense, Grace?
Yeah.
Which one else?
8.
The limit as, now this one's different because x is approaching 0. Right? So this is a tricky one. It's, when I plug 0 in, rule number 1, plug it in, 2 minus the square root of 4 plus 0 over 0. See how I get 0 over 0? So this is one of these that's a conjugate. Whenever I have that radical, I'm going to go ahead and multiply both the top and bottom by the conjugate. So 2 plus the square root of 4 plus x over the 2 plus the square root of 4 plus x. So here's what I get. When I go to multiply, my first terms is 4. My inner and outer cancel out. Then I have minus 4 plus x, because the square root of anything squared is that radicand. Are you okay with that minus sign being there? So here's the secret to the conjugate ones. Don't multiply your denominator. Because what's going to happen here, are you ready? What's going to happen here is this is going to be, next step, 4 minus x over x times 2 plus the square root of 4 plus x. 4 minus 4 is 0. X divided by x is 1, which is going to leave me with negative 1 over 2 plus the square root of 4 plus x. And somebody said to me when I was working with them on this, they're like, wait, I don't get it. How come it doesn't work out initially, but now it does? What changed? And it's all about this sign that changed thanks to my conjugate, because I used to have a minus, but I gave it a plus. So when that conjugate is able to be simplified in my numerator, I'm able to eliminate this x that's messing me up. I'm able to give myself a positive sign here so that when I have -1 over 2 plus the square root of 4 plus, remember x was approaching 0, square root of 4 plus 0 is 2. So that's how I end up with -1/4. Does that make sense, Grace? Okay. On the back, 9 and 10. Again, which calculus student are you? Are you the one that did your homework? Are you checking your answers? Are you the one who hasn't done your homework yet? But you're going to. So you're going to write the answers, and you're going to put a little box around it. And when you get around to doing the practice that you need to do in order to learn your calculus, if you can't figure out how that answer matches mine, that's when you come in the morning, you come in after school, no judgment. You're like, hey, I'm still doing homework from 2 days ago, it turns out. I've been there. But this is the one I don't understand. That means that you don't get a chance to ask the question in class. You got to come before school or after school for us to figure out where you need to make some fixings. 11 and 12, here's 13, 14, 15, 16. Or you gonna watch the video? Because now that I'm videoing, you're like, just post the video, lady, and we're good to go. All right, any of these you want to see? Oh, lots of hands. Go.
16. Here's your calculator.
Oh, I was looking for that. Thank you. Go for Smarty Up. All right. 16. He says, as x approaches 0, Anthony, step number 1, I have 1 over 0 plus 3 minus 1/3 all over 0. That gives me 0 over 0, and I'm crying because that's not allowed. That's my indeterminate form. Hey, the word indeterminate means I can't determine it. Try that on your mom and dad next time they ask you, hey, when are you coming home? That's an indeterminate form, Mom. It can't be determined. All right, so something has to change, Anthony, and that means that I'm going to take a look at and try my common denominator strategy. When I look at my common denominator, it's got to have an x plus 3, and it's got to have a 3 in it. Are you okay with my shortcut of how I do this, or do you need me to spell it out more specifically? Because I just give each fraction the factor that they're missing. This guy needs a 3, and this guy needs an x minus 3. Are you okay with that shorthand, or do you want me to do it long ways? Long ways. Are you ready? 1 over x plus 3 minus 1/3. When I want to find a common denominator, each factor needs what the other guy is bringing to the table. You okay with that? So I'm going to multiply this guy by 3 over 3. That's going to give me 3 over 3 times x plus 3. Are you good with me now? And I did this in algebra 2. Kid raised his hand right now and goes, oh! I'm like, what's on your mind? He goes, cancel those 3s out. I just put him there. Well, but I cancel them out. But thanks for playing. This guy needs what this guy's got. 3 times x plus 3. So I gave him an x plus 3, and that's because x plus 3 over x plus 3. I can multiply anything by 1. That's my multiplicative identity. Remember learning that in like the 5th grade? And you're like, why are we learning this? Because in 7 years from now, you're going to be doing calculus and finding common denominators. So now 1 times x plus 3, and I'm seeing where Billy's going. Should I beat you to it?
Well, I was going to say that.
You can put a Smarty up. Are we good now? So then we have in my denominator, my common denominator, looks like this. And this is 3 minus. And I'm always going to bubble wrap this, especially when there's a subtraction sign, because I need to distribute that negative to both terms in the expression. We okay with that? All right. Now that Billy found our problem, here we go. And by the way, this is all over x. So 3 minus x minus 3. And by this point in time, we're not surprised when that works out, because that's the whole purpose, right? These problems, my friends, are designed to work out all over x. So 3 minus 3. Now, do you want to see this division, or do you want me to, are you okay with this? See you later, x's. That's going to give me a negative 1 over 3 times x plus 3. When I plug in my 0, it now works out. These problems are designed to work out. If they don't work out, you can count on me or Miss Holloway having a typo. You're like, oh, double check this one, because these ones work out like that. Okay, what else do you want to see from this homework? Go, Steven. 11. Okay. 3 times the sine of 1 over x as x goes to infinity. So when we look here, we go back to our sheet for our trig rules. So we go all the way back. Jacques, did I give you one of these pieces of paper?
Yeah.
Our trig rules for limits. So as sine of x over x, oh, wait a minute. That's not going to work out, because that's not my special trig properties. I wonder if I need to do what step 1 is and just do what? Plug it in. How do I plug in infinity? So when I put infinity in for x, that becomes a super, super small number. You buy that? If I put infinity in for x, go with me here. If I put 3 times the sine of 1 over infinity. Now you're like, you can't do that. I'm like, hang on a minute. The bigger my denominator gets, what is this number approaching? If I looked over at my trig circle, what is my sine of 0? So then 3 times 0. So I had a poster hanging in my room in the past, and I thought of it, it reminded me of what we were doing with limits, so I thought I would put it up here. And I don't know if you can see it or not, but it says this. A man is like a fraction whose numerator is what he is, and whose denominator is what he thinks of himself. The larger the denominator, like that? It is an actual quote from Count Leo Nikolavich Tolstoy. Leo Tolstoy. Thanks, Leo. Thanks for giving us a lesson in humility. Right? I don't know. Maybe that'll help you remember infinity in the denominator. Maybe? As you approach the Okay. Anything else for the homework? Yeah.
Number 10.
Okay. The limit as x approaches infinity of 4 to the negative x. So 4 to the negative x simplifies to that. Plus 1. Are we okay?
Yeah.
So what we're gonna do is we're gonna start understanding as this goes to infinity, that morphs into 0. Yeah.
15.
Which one?
15.
15. Mrs. Fisher, can you do my homework for us? Sure. Oh, I love this one. Ready? This one's tons of fun. Now, rule number 1, plug it in. You're gonna get 0 over 0 because of how this works out. So I need to do some algebraic manipulation. Ready, Grace? This one's tons of fun. Do you see that the sine of x can be factored out?
Yeah.
Do you see how you have the cosine of x minus 1? Now watch what I do with my x's. This is so fun. Are you ready? Oh, do you see it?
Yeah.
What am I going to do?
I forgot to GCF it.
So I can kind of split those x's. Now go get that form. Go get that reference sheet. Because the sine of x over x is 1. And what is the cosine of x minus 1 over x?
0.
1 times 0?
0.
Bam! Kind of cool, right? Okay. You're like, hey, if we ask enough questions, then she'll never get to today's lesson. I'm like, hey, doesn't look like I'm getting to today's lesson. But I need to. So on the quiz, a bunch of people lost points on conversations about continuity. So up until you were in calculus, when you were in all of your other classes, algebra and pre-calc, they had you define continuity as, can you trace the graph with your pencil? And that's why half of you forgot it, because you're like, there's got to be something more than that. There is. Is there anything in paper? Okay. Okay. You have to do it.
Oh.
I'm kidding. Alright, so a function is continuous if its graph is a single unbroken curve that you can draw without lifting the pencil from the paper. So give yourself a couple examples of functions that you know are continuous. Your linear function, continuous. You thought it meant it went on forever and ever. So as long as you can draw the whole thing without picking up your pencil. What about a quadratic function? Continuous? Yeah. What about a cubic function? Continuous? What about an absolute value function? So being able to continue on forever and ever is not what we're talking about. What we're talking about is, can you put your pencil on the graph and trace it, the whole thing, without picking it up? You have colored pencils in your baskets, so grab one. Can you trace this entire graph without picking up your pencil? No, there's a hole in this graph.
Fine.
Any Big Fat Greek Wedding fans? There's a hole in this cake. You ever see that movie? We love that movie. We quote that movie all the time. Homework. Watch my Big Fat Greek Wedding. There's a hole in this graph. All right. Second kind of discontinuity is up. I need to jump. So it's not just about there being a hole. It's not like something I can like step over. Oh, sorry. And then keep going. Look at this. I need to actually jump. Our next kind of discontinuity is where we have an asymptote, where as you approach a value, the graph goes in completely opposite directions. So at our vertical asymptotes, our graph stops being continuous. We can identify where the functions are discontinuous by locating the holes in asymptotes. So just as a reminder, our vertical asymptotes are where your denominator equals 0. Your wholes are going to be when a value of x factors out and can be canceled. So when you lose an x, that's when that whole happens. So when I look at this graph here, x over x plus 1, I know that there's a vertical asymptote at x is equal to negative 1. What are we laughing at? I want to know. I want to be funny too. There's your sketch. So it makes sense to me that this graph has this vertical asymptote at x is equal to negative 1, because that's where that graph has a denominator equal 0. Stop, ready? That's also where we can look at the horizontal asymptotes. I have that my x is in the same power, so that's like having infinity over infinity, right? They cancel out, so my coefficient's equal to 1. Do you see this horizontal asymptote of y is equal to 1? Yeah, that's kind of cool. So if I want to draw this one, if I want to sketch the graph, I know I have my horizontal asymptote is at y is equal to 1 because my powers of x are the same. And that graph heads like that forever and ever. Are we good with that? Yep. Right. So let's look at our next example. Sometimes we need to make sure that we factor. So if I have x squared plus 1 and x squared minus 1, I can look at all of these different factors of x and check it out. My numerator and my denominator have a value of x that I can factor out and cancel. Every time I lose an x from my denominator, that's a whole. So my whole is going to happen when x has an input value of negative 1. Because if the fraction stays originally like that, negative 1 is going to give me a 0. Or is going to give me a 0 in the denominator, which is undefined. When I'm looking at my vertical asymptotes, I know that x cannot have a value of positive 1. So I know that at positive 1, that graph is going to stop being continuous because it's going to go in opposite directions forever and ever and ever. Now, if I'm sketching the graph, it's nice to be able to look at and see where our horizontal asymptote is. I have more x's in my denominator than in my numerator, which means y is equal to 0 is going to be my horizontal asymptote. Are we good so far? Let's pop over to Desmos, and we'll take a look at the graph. So we'll turn this guy off. See you later. Turn this one on. Did I have that one right? I did it backwards in the notes. How come nobody said anything? This one I did backwards. I did backwards in the notes.
No. No.
Yes.
Oh.
Yes. Thanks for paying attention, friends. I guess you guys really don't like candy. What? That's better in the notes. Thanks for, you're killing me. Let's turn this one on. Turn this one on. So here's what's cool about this. Are you ready? I told you -1 was where my hole was. And if I look here, I can see where the hole is. But what I want you to do is watch what happens when I drag this along and I hit -1. Oh, hello. There's my hole. But notice if I wanted to fill the hole, I can with this point. Because when I'm looking at this function, after I removed it, I can go ahead and substitute -1 in without worrying and get a value of -4. What was it, -1/4?
Yes.
So we can tell everybody where the hole is. And this one went this way. Are you going to fix me if I'm wrong? And we know that at -1/4, there's a hole. So unless we take the time to graph it in Desmos and zoom in on everything and slide it along, we might miss this stuff, which is why, thank goodness, we have the algebra on the back. Oh, there's a trig function. And you're like, yay, we were missing, we were hoping. Hey, instead of tangent of x, why don't you think of it as, say it with me now. Why don't you think of it as sine of x over cosine of x, and your vertical asymptotes are going to be where the cosine of x is equal to 0. Because that's when your denominator goes to 0. So if I look again at my unit circle, every time that my cosine is equal to 0, that's going to be at my pi/2 and my 3pi/2. And that's going to give me my asymptotes as I go. Remember your dancing? I had a tutor one time, I called them dancing snakes as they go on. So our asymptotes tell us where this graph is not continuous. Hey, don't forget about the easy ones. X² - 1, that's a parabola. It's continuous. It has no holes, no jumps, and no asymptotes. So if you have a regular graph, it's okay. There's the possibility for that graph to be fine. Hey, here's our formal definition of continuity. In order for a function to be continuous, 3 things have to be true. And we have to know that the limit is equal, that the limit exists. And keep in mind, we just talked about the limit exists if it exists the same from the positive and negative. So number one, is there a limit? Number two, is there an output value for the input? Number three, do they match? So if you fill in those little boxes, when we talk about f of c is defined, inside that little box, write the phrase no holes. Because we want to make sure that f of c is defined. That means that there are no holes. If the limit exists, that means it exists from the left and the right. It matches from the left and the right. By the way, those things have to match. So let me get this real quick. Are you ready? F of c is defined. That means that there's no holes. There's an output for the input. The limit exists. So the limit from negative and positive match. That both of these are the same. The value of function, think about it in terms of the output, is the same as the limit.